Alright, the second part of this topic is basically on protein purification prior to separation. So, well, I've juggled this to be put in front and then sometimes at the back. So this time around I put it at the back. Okay, even though purification is usually done in the beginning before separation, but a lot of times, okay, because we're going to talk about, okay, and this section is specifically for chromatography. So chromatography is most of the time done after you have identified your protein which makes after separation, and then only you do chromatography and then you separate a lot more, okay, so that you could really separate it and you get your one true purified protein. Hence, we have it after the separation. So let's move on to the steps on the protein purification itself. So first and foremost, you need to choose your protein to purify, and hence you need to determine your proteome first. Second, you need to choose your source, whether it's going to be natural or expressed protein. So there's a difference between the two. The third one is whether it's going to be soluble in aqueous solution or not. So you need to be very careful, especially with membrane protein, which could be, I would say, a bit problematic to a lot of people. Number 4 is stability. So protein stability vary. Again, it doesn't mean that protein which are non-soluble or those that are soluble are stable. So it basically depends on the protein structure itself. Number 5 is purified, okay, which is based on some characteristics of the protein. And of course, the last one is the downstream process, which is the study, whether you want to study the activity, the structure, the mechanism, or the action, and etc. Right, so the purification methods again is of course based on its characteristics. So I've put 4 characteristics as you can see on your left, okay, the column on the left, and these are some of the procedure on the right that is related again to the characteristics. So as I was saying, so this part is solely on chromatography and some method for purification. So you can see that the procedure are related to chromatography. For example, charge, because we know protein, some of the proteins are charged. So the most common that we will use is ion exchange, which we will cover. So there are 2 types of ion exchange, anion or cation. Okay, you can also purify it further by gel electrophoresis, but usually this is not recommended because chances are you will not get high purity as compared to using chromatography. Another thing is that you can do isoelectrophoresis. The downside is that you need to do a lot of 2D gels later on, and you need to make sure that you have sufficient quantity. So based on the size, the characteristics of size, okay, these are the procedures: dialysis and ultracentrifugation. So dialysis we will cover as well. It is not a part of chromatography, but it is a procedure to purify, another method. And ultracentrifugation, you may have heard of centrifugation, centrifuge, okay, and you may have used it, but ultracentrifuge is something different. So the name ultra, which means that usually the RPM is more than 100,000, so that means that it could more or less separate your particles, okay, during the centrifugation itself, whereby normal centrifugation couldn't. Secondly is of course gel electrophoresis, could be based on size, we know that, but again probably not a very good purification method like I said previously. The third one, which we will cover, is gel filtration chromatography, which is also referred to as size exclusion. Oh, I have double ultracentrifugation here. Alright, so for the specificity, there's only one procedure for it, okay, because specificity is very specific, okay, so we only have affinity chromatography, and based on polarity, there are 4 procedures. So for chromatography, we to choose from adsorption chromatography, paper chromatography, reverse phase, and also hydrophobic chromatography. Alright, so let's see the general procedure of protein purification via chromatography. So we know that chromatography is a common method, okay, widely used to separate proteins and also sometimes some other substances, but mostly is for protein previously. So it is an important purification technique since early 90s. And color chromatography, okay, is used to isolate proteins. So there is a linkage over here, okay, if you're interested, copy paste, okay, and then watch it on YouTube. The mix of proteins, okay, because when you extract protein, the protein is a mixture of proteins, lots of protein in there, so they are loaded onto the column that contains a matrix or resin. So the matrix usually comprised of resin or some other substances, and separation will occur because protein interact with the matrices or the resins in different way depending on the characteristics that you choose from. So these are the steps, okay, in chromatography, and these 5 steps are quite common, okay, and in terms of packing the column, the first one, okay, whether you do it yourself or you buy the pre-packed column. So if you have a lot of money, buy the pre-packed column. If you don't want to spend that much of money, usually it's thousands to a few, more than about 10,000 to 20,000. So you can prepare your own column, okay, by packing it. So column could be packed with material, okay, which is often a resin that could absorb the molecules based on the property such as size, charge, binding affinity, and also polarity, the four characteristics that we have seen in the previous two slides. Secondly, you need to equilibrate the column. So equilibrate column meaning that the column is washed with several column washes, okay, which means that you use again buffer. This is to make sure that they are ready for their separation, okay, afterwards. Third is of course you load your sample and you apply the sample mixture, okay, to the column, which means that you just load it in there, okay, and then you let gravity take place. Afterwards, okay, you wash the column, okay, after it has passed through the column. So molecules will be washed through the column with buffer, okay, and the buffer depends on the type of column and also based on the property. Lastly, you collect the fractions, and fractions are usually taken at some point of whereby your molecule will elute, and it also depends on the type of chromatography being applied to. Now let's have a look at the first chromatography. So first one we have size exclusion, okay, or also referred to as gel filtration. Chromatography is actually more known as size exclusion because it's actually separated based on size. So the column is packed with porous beads. Well, beads that you couldn't probably see well, okay, with your naked eyes. So when washed with buffer, and of course get different pH, okay, and certain basically recipe for the buffer. So small molecules, okay, will enter the beads, okay, and of course larger molecules will move between the beads or pass through the beads. So later on you just elute the column, where large proteins, okay, which will elute first, okay, small protein less because the small protein is the one, okay, that is trapped in the pores of the beads. So the shape of a protein, its quaternary structure, and also other associated proteins will of course affect its apparent size in solution. And this of course is not recommended for separating proteins with only a small difference in molecular weight because chances are you will not see or you will not be able to separate it well. So the choice of a chromatography matrix is also an important aspect in gel filtration. Most of the time the matrices are gels from polysaccharide, okay, dextrins, that are usually formulated into the beads, okay, they make it into the beads, okay, each with different matrix, okay, and of course have different varying degree of cross-linking, okay, of the dextrins. And of course, okay, later on, okay, they will form pores in between them. Alright, so based on this picture, okay, this is basically a representation of the beads being used in the size exclusion chromatography column. So like I said, okay, you won't be able to see the pores, okay, but the beads, okay, there are pores, okay, in between them, or all around the beads, simply said. So proteins larger than the exclusion range of the resin cannot enter the pore, so or they are bounced back, which means that they couldn't enter. Only the small molecules, okay, could enter and probably trapped inside the beads. So this is what happened based on the principle of size exclusion. So that means that again the larger molecules, okay, will be eluted out first, okay. The smaller molecules, okay, you have to elute out fast, okay. Later. So that means that you need to make sure you know the exact size to use, and also that is compatible, okay, with the size of the beads. Okay, so the second one, okay, so this is based on basically charge, okay, which is ion exchange. So like I said earlier on, we have two types of ion exchange chromatography, either cation or anion, okay, positive or negative. And of course, okay, since this is separated by charge, okay, the column, okay, will be packed with the charge resin, whether it's positive or negative. And of course the buffer, okay, usually are also charged. How? Usually is because of the combination of the solution. So charged proteins, okay, will flow through the buffer, whereby oppositely charged proteins will bind to the column. Okay, so that means that you need to have the opposite charge, okay, packed into the columns that will bind to your protein of interest. So let's say if your protein is negatively charged, okay, so your column have to be positively charged, right? So because the ones that bind to the column, okay, you will elute it last. Okay? So when you elute the protein, okay, you will know that, okay, you get the protein which is the opposite charge, okay, from your column. So how do you elute the protein? By increasing salt or pH to elute the protein of interest. And a bit of a downside again is that, well, if you have a few proteins which are charged, okay, at the end you actually get a few proteins. But okay, if you have one target protein and you basically have done a purification, other purification prior to it, you will get one good purified charged protein. Only that one protein that you desire. So again, okay, representation of ion exchange chromatography. And there's a link over here. You can just copy and paste and view it via YouTube. Alright, so let's have a look over here. Okay, like I said, we have cation and we have anion. Okay, a chromatography, okay, which is based on the exchanger. So that means that, okay, for cation exchanger, okay, your net charge of molecule of interest, okay, will be positive. Okay, cation, we know, okay, and anion is negative, so it has to be the opposite charge of resin. Remember, don't put, okay, positive with positive, because what happened? Nothing will happen. Okay, because say it means that, okay, we will repel each other, it will not bind, so you will actually wash off this one, okay, to the first one, okay, and if you are not careful, you may just throw it away. Okay, so what will bind to is the one that is the opposite one. Right, so these are some of the running conditions, as you can see. Okay, and remember, okay, usually, okay, we just increase, okay, either the salt, okay, or increase the pH, or both, okay, during the elution of the final step to get your correct charge purified protein. The third one I'm going to cover, okay, is based on the specificity, okay, the third characteristics. And like I said, there's only one chromatography, which is the affinity chromatography. So for affinity chromatography, okay, you have to remember the lock and key hypothesis or theory, okay, in the first topic last week. So the column is of course packed with either molecules or ligands that interact strongly with the protein of interest. You need to find that out. If not, then you're going to blunder everything. So during the wash, again, the molecules of interest will bind to the column. Of course, that is the reason. Okay, we want it to bind to it first. Okay, and we let other proteins flow through. Okay, so the last step is that we elute it. Okay, so the bound proteins will be eluted by adding higher concentration of the ligand. Okay, so that it binds strongly to the ligand. It basically just pulls it out from the resin. So the next one, okay, is basically a machine, okay, which is fast protein liquid chromatography. So this is a machine, okay, whereby you can separate proteins or purify proteins, okay, based on polarity or charge. Okay, so you can use size, charge, affinity, or hydrophobicity to also purify depending on the column, because the machine is just there for you to use, okay, and you can basically just change the column, as you can see over here. Okay, so but you have to remember, okay, because you can actually do more than one chromatography at one time, so it will have low pressure, so it will take a longer time to pass through the columns. But well, good side is that you could actually do more than one purification at one time, okay, and also you can use different you can basically separate it based on different characteristics depending on the column that you want to use. Alright, so the next one, okay, which is actually on the last characteristics, okay, is on paper chromatography. So alright, so you guys are from SMBB, right? So you have done paper chromatography in your second year. So remember back second year, the Talina's class, okay, which is on plant physiology, if I'm not wrong, plant physiology, right? Because I did help out with the lab practical a few years ago. Okay? So for paper chromatography, okay, so remember back how you do it, okay, with carrots and so forth, okay. So we use filter paper as carrier, and separation is based on partition between two immiscible phases. So the first phase, okay, is the water, which acts as stationary phase and of course absorbed in the paper. So the second one, okay, is the organic solvent, okay, which is also actually a stationary phase, but it flow past the sample on the paper. So what you will see, okay, is actually, okay, when the solvent pass through, okay, you will get, okay, different color depending on the pigment available in your protein of interest, if there is such. So remember back, okay, this is how you do your chromatography. Okay, probably not in this entrapment, but more or less similar. Okay, you do it in a beaker, you put it in there, okay, and then you just, okay, see how the migration goes through, and then you basically measure, okay, the distance, right? Okay, so I think either this is the last or the second last. Okay, so reverse phase chromatography, okay, also known as adsorption chromatography. So when you see adsorption or reverse phase, they are more or less similar, but in a way reverse phase is much better as compared to adsorption. Okay, Why and how? Well, if we have the time, probably we could discuss it, or you could remind me during the online class. So, this kind of chromatography depends on the chemical interactions between the solid molecules and also specific ligands, but it is different from affinity because this is basically based on polarity. So, binding of mobile phase solute to an immobilized alkyl hydrocarbon or ligand usually occurs through hydrophobic interaction. So, your insoluble beaded matrix has to be hydrophobic ligands, and the base matrix is usually from silica or polystyrene. So more or less you could basically this is how it is going to be separated, and usually it has to be done using an HPLC machine. So what happens in reverse phase chromatography is that you have a stationary phase, which is your column, and you have a mixture of components from your protein. So the flow of the mobile phase is as such from here when you pass it through the column. So you have to imagine it the other way around. So usually it's vertical, right? But this is basically horizontal. So once it passed through the column, what happens is that the most hydrophobic component interact with the column best, because remember from here, hydrophobic interaction. So the least hydrophobic component will be eluted first because it doesn't interact, it won't be retained in the column. So you elute the product of your interest, and hence you have to make sure when you use reverse phase chromatography it needs to be something that is hydrophobic or hydrophilic. Should be hydrophilic, right? So so most hydrophobic component will elute last. Now the last part is actually on purification by dialysis. So it's not kind of, I'm not sure how your understanding of dialysis is. So dialysis means that basically it is based on separation of molecules based on size. But this is could also be one of the way to separate proteins based on size, but more or less this is not as efficient as size exclusion chromatography, but it could be used because it's cheaper. And if if you don't care about the size of the molecule, you just want to separate based on whether the large and the small, then it's fine. So this is basically the definition of the dialysis. So it is through the use of semi-permeable membranes containing pores of less than macromolecular dimensions. So the pores in the membrane allow the solvent, salt, and small metabolites to diffuse across but block larger molecules, as with the case. So a lot of time cellulose acetate or cellophane is used in dialysis material. The material basically, as you will see in the next slide or in your notes, we basically use, it's not a column, it's kind of like a plastic. Any one of you who have seen ice cream Malaysia, I hope there's no international students in here, or probably in some Indonesian. You can ask your friends, what is ice cream Malaysia? So usually it's in a long plastic, kind of like that. So the dialysis tube is like that. So it is usually used to change the solvent in which the protein is dissolved in. So hence that's why I say it's actually not really that good to really separate the protein well. But it can also be used to concentrate a protein solution by placement in a polymetric desiccant such as PET, polyethylene glycol, which cannot go through the membrane, but it absorbs water through the membrane. So because polyacrylamide is basically have that requirement. So this is what happens, and that's why I say so if you can imagine at the ice cream Malaysia, so the membrane or the dialysis tube is as such. So you just tie at one end first. Well, you can tie or you can just clip it. There is a link over here to a video in YouTube. In the video I think you will see that they will clamp it, and that's what I did. I actually didn't tie it, I basically clamp it with a bulldog pin. So at the start of the dialysis, afterwards you just fill up your protein, and then you tie the other end. So your solvent have to be something that is either higher pH or lower pH than your protein solution. So you need to know the types of protein, the pH as well if possible, or at least the concentration that it reacts to. So whatever happens is that during dialysis at equilibrium, when everything is at equilibrium, the smaller proteins, okay, will diffuse out, okay, from the dialysis tube. Okay, how it diffuse out? Remember the theory, okay, from here. Okay, is that there are pores, okay, just not visible with your naked eyes. Okay, try as you may, or you might, okay, you will never see it. Okay, don't worry, I've tried, I've used it on the magnifier even. I actually couldn't see the pores, but okay, smaller proteins, okay, will usually, okay, be diffused out, okay, into the solution in the beaker, and then you are left with the larger molecules inside here. But the downside is that sometimes some of the smaller molecules can also be retained inside. So you need to adjust, do a trial and error in terms of how long you need to leave your protein in this solution. Then afterwards, okay, what you can do, okay, is that you can just take out the tube, okay, transfer into centrifuge tube, and then centrifuge it. So the debris, okay, that you get, okay, is actually your protein, and then you can just dissolve it in your buffer or whatever dissolution solution that you want to use. Alright, so there you have it on the chromatography. Very lengthy, but like I said, very simple. So for next activity, okay, be prepared, and I'm telling you now, okay, but I will explain it later on, especially via e-learning. We will have a chromatography contest, so be prepared for that. See you.